So the thing we start with is Dirac notation. So we have a whole bunch of matrices that we should know. So we have our computational basis state. So we think of a quantum state as vectors and the gates as matrices. And so we have computational basis vector where in 2 dimensions we label them with 0 and 1. Okay, so 0 and 1, and 0 is this 1, 0 state, and 1 is this 0, 1 state. And then we have our 3 most important matrices, where Y is kind of not important because it has I and we don't quite like it. But anyway, so there are sigma X, sigma Y, sigma Z. And they have different names. So one of the names is big X, big Y, big Z. And sometimes they also call sigma X, sigma Y, sigma Z as written here. And there are those 3 matrices. So X is 0, 1, 1, 0. Y is 0 minus I, I0, and Z is 1, 0, 0, minus 1. And also now let's pick back to a little thing, something that we want to say later. And we also like to think about what they do on computation-based state because this is useful when we do circuit calculation. So, and yeah, here we kind of see we like X and Z more because Y we kind of think as a product of XZ. But anyway, so X on a computational basis state A, it will become A plus 1. So we have this O plus, it all means mod 2. And Z on computational basis state A become minus 1 to the A. Okay. And okay, so those are poly X, Y, Z. And another also very important matrix is this head mount. Okay. And written in matrix form is this, what's going on? 1 over square root 2 of 1, 1, 1 minus 1. Okay. And it's really nice because it is transformed between the plus minus state and the 0, 1 state. So H on 0, 1 become plus minus, and H on plus minus become 0, 1. Okay. And those plus minus state are the eigenvectors of X. So plus state is 1 over square root 2, 1, 1, minus is 1 over square root 2, 1 minus 1. And yeah, sometimes we are lazy and don't write 1 over square root 2, but if you do that, you need to remove your normalization in the end. And H squared equals identity, and I think we have seen somewhere that H can be seen as a generalized poly. We'll probably do that later. And yeah, so as we say, H, so plus and minus is plus 1 and minus 1 eigenstate of the X operator, and 0 and 1 is plus 1 and minus 1 eigenstate to the Z operator. Yeah. And then there's something special to remember, that is when you do the transpose. So when you write the column vector and you do this dagger operator to get the corresponding row vector, then you need to do complex conjugation. So this dagger is transpose, then complex conjugation. This is special because we are doing complex numbers. So for example, it's 1i column vector. You do dagger on it, and it becomes 1 minus I. So this minus I you need to remember. Okay. And so this doesn't happen when you do on this 0, 1 state or plus minus state. So when you write a broad, then it's just a transpose because they are all real. But when you have complex number, you need to remember the minus sign. Okay. And yeah, as we say, computational basis. Well, computational basis for qubits are just like the standard basis, and so it's a basis labeled by it's either integers, and we in computer science we count integer from 0, and so if it's qubits, then we just label it as a bit string, so 0, 1 to n, where you have n qubit. And in 1 qubit, the computational basis is 0, 1, and 2 qubit is the 4 possible string, etc. And you can generalize yourself to more bits. Okay. And then we talk about more gates. Okay, so 2 qubit gate is C0. C0 is the most usual qubit gate we see, and it has multiple good things about it. First, it's a classical gate. So remember classical state to a classical state. So remember computational state to a computational basis state. And yeah, and we have also seen that from CNOT and 1-qubit gate, you can build a universal quantum gate set. So yeah, people like CNOT a lot, and there are even a little more structure that we won't talk about here. It's called Clifford group. Yeah, let's not go into that. Okay, so for review, CNOT is defined as this thing, so it's a control X. So if the first qubit is 0, then you apply nothing, and first qubit 1, you apply X on the second qubit. And you can think about why X on the computational basis. So AB become A and A plus B. Okay, so you add the first qubit to the second qubit. And then we can think about control NOT, and it's called Toffoli gate. And it's basically the similar thing, but you apply X on the third qubit only if the first qubit are both 1. Okay. And so if you write it in terms of this computational basis, ABC, then ABC become ABC plus AB. Okay. And then we also have control Z. So control Z has this interesting symmetric notation. It has things like it has 2 control qubits, but actually, so this actually either one of it can be seen as a control and the other one be target. So you can think this is control Z. So if you think the first one as a control is 0, then you do not think it's 1. You apply Z gate on the second qubit. But see that is actually symmetric because you apply on AB, then it's -1 to the A times B of AB. So this A times B means only happen when both A and B equal to 1. Okay. And we have swap gates look like this. Okay. So it's a cross. And so AB become BA. Then also we can have similar to control now, we can have the control Z, although we didn't quite have a later note, but we have this also. So control Z is also symmetry in all 3 qubits, and because if you write down its action on computational basis ABCC, then it's -1 to ABC. Okay. So those are gates. And okay, so we are in funny direction. So we talk about all those matrices first, then we go to Dirac notation. Okay. And yeah, as we said, Dirac notation, we have those bra and the kit. Okay. So bras are basically column vectors, and once again, it's so bras are things with this shape. Okay. So this thing a straight line and have a bracket. And we have sorry, it's a kit, and we have a bra. So have for the bracket and a straight line. Okay. And as we said, so we have the same symbol, and we can think about this is the dual vector. So the row vector is the dual vector of the column vector. And so this is a column vector taking dagger, and as we said before, you need to do the complex conjugation. So not only you do transpose, you need to do complex conjugation. This is because we want the row vector, so we want the bra vector times the ket vector itself. You want this to be inner product with itself. We want to be a non-square, and non-square should be a positive real number. That's why you want a complex conjugation here. Okay, and yeah, so Bragg notation that we see we can combine whole bunch of them together, and they all make sense with each other. So we write them together, and sometimes if we have 2 straight lines, we'll combine them. So here is the inner product, and you can also write the 2 straight lines as 1 straight line. But anyway, so we list them together, then we kind of think it just as matrix multiplication. So the psi bra times phi ket is just a row vector times a column vector, and it become number. And you can also have outer product, so you have the phi bra times the psi ket. So it's a column vector times a row vector, so this will become matrix. Okay, so I will write the result, and so this is one number, and this is a matrix with rank 1. And then we also have this thing that you probably didn't see in linear algebra course, is tensor product. So you can tensor product 2 matrix, 2 vector together, and it will become a vector on a much bigger space. It's on the tensor vector tensor product space. Okay. And so basically, if it is d-dimensional, it is d-dimensional. So maybe I should say it's a-dimensional. So if it is a-dimensional, b-dimensional, this will be a b-dimensional. Okay. And yeah, well, it's kind of like this. So if it's 2 by 2, then the first vector here and times the first element of the second vector and the first vector again with multiplied by the coefficient of the second vector, etc. Anyway, yeah, you can look up the previous slide to remind yourself the definition of this. And okay, and we have a few examples. Okay, so the easier one, we don't have an example for this. Okay, so maybe let's do an example of this because it's harder, right? So we can have like 1, 2 tensor 3, 4 equal 2. So the 2 by 2 will become a 4 by 4 vector. So 1, 2 times 3, so 3, 6, and then 1, 2 times 4, it becomes 4, 8. Okay, any question? I believe the notation is consistent with what we have. Okay. And yeah, the easier example, so plus and minus, and so plus ket times minus bra, and so it is column vector times is row vector, and you can do this outer product, and it's just by matrix multiplication rule, and it becomes 1 minus 1 minus 1 1 minus 1, and also we have a 1/2 outside. And then okay. And then we have more example about tensor product. So we have a tensor product of vectors and times the tensor product of matrix times the tensor product of bra vector all together. And when we have a tensor product thing times tensor product thing, basically you do the 1 slot by 1 slot. So this so we have this okay. So we have this really weird thing. So it's a bra vector tensor the identity matrix. It looks like kind of ill-defined, but actually it's doable because you can still multiply it on this vector on tensor product space, and it's just defined by, as we say, slot by slot. And so you have this thing multiplied by this thing, then you will have the first slot multiplying each other together, so this becomes number, and the second slot is just identity on 0. And because the first slot become numbers, so basically that register just vanish, and you are left with a vector on second slot. Yeah, so now it's just a vector on second slot, and well, it's identity on 0, and also a number from the first slot give you its inner product of minus and 0 is 1 over square root 2, so you're left with this 1 over square root 2 1 0. Okay. And yeah. I have more example. So this is like what happened when you measure. This is when you measure x on region x. So think about you do a measurement of the x operator, then you are measuring a basis of plus plus and minus minus. And so if you measure x on first register. And then we have our favorite entangled state beta 0 0, and so this happened, and so we are thinking what's the subnormal state when you get this plus 1 eigenvector. Okay, so it has plus 1 eigenvector and minus 1 eigenvector. Okay. So on plus 1 eigenvector, then the subnormal state is you project onto plus 1. Is plus project onto plus state on first register and do nothing on second register, so close identity. And you apply this on the entangled state, then you by linearity. So you apply on 0 0, then you apply on 1 1, and do the same similar thing we do before. So plus plus on 0, it becomes a plus state plus, and you got 1 over square root 2 from the inner product and 1 over square root 2 from here, so 1 over 2, and the identity on 0 becomes 0. And similarly, plus on 1. It's also 1 over square root 2, and they also become plus. And the second register stay 1. Okay. So you see, well, the first register got projected onto plus, so obviously it all comes out with plus. And then you combine those two things, so it's 1 over square root 2 plus. And tensor with, so it's like tensor here. Tensor with 1 over square root 2 of 0 plus 1. And this is another plus state, so it's 1 over square root 2 plus tensor plus. Okay. And yeah, so now it's a summarized state. So if you think about this as a major in X beta 00, then you'll see with the parameterized state of probability will be 1 over square root 2 square 1 over 2, and the actual state is just this part, okay, plus tensor plus. Okay, this is an example of measurement. Okay, and talking about measurement, then let's review measurement once again. So as we said, there are a lot of measurements, so we actually have 4 of them, but actually, anyway, so we have like 3 forms of measurement. So there's a 0 of computational basis measurement, which is very obvious specialization of the first one. Okay. The first one is you measure on orthonormal basis EI. Okay. So you measure your pure state, and well, on orthonormal basis EI, then you basically just write this with a basis, is a basis, so you can write your state as a unique linear combination of your basis element. So you write as this linear combination, and then the probability of each outcome will just be this AI square, the coefficient absolute value square, and yeah, that's the probability of you get outcome I. And if you get outcome I, then your state will get collapsed into EI. So this is also normal basis measurement, and most of the time you will do this on computational basis. So 0 to d minus 1, or sometimes 1 to d. Okay. And then you can also measure operator. So operator is a Hermitian matrix, means A dagger equals A. And if it's Hermitian, then you can diagonalize it into with some I lambda I. So lambda I are eigenvalues, and those projector. And those kth or bra lambda I are the eigenvectors. So yeah, so it diagonalizes into the projector onto eigenvectors and the eigenvalue times eigenvalues. Okay. And so when you measure this thing, is like you measure in those eigenvector basis. Okay. And when you get outcome I, then we think we get the value of the operator lambda I. Okay. And one thing you can prove is that the expected value of measure this thing A on some psi. Okay, so this notation is a bit funny because sometimes we omit psi. Okay, yeah, usually it's clear. But anyway, so you measure some psi on this operator A, then the expected value will be the sandwiching of A between psi. So plus psi A k psi will be expected value. And then there is a funny thing about degeneracy, that is, okay, so we're saying this is just measuring orthonormal basis, but sometimes you have degeneracy, say your A equal to just a thing we see before X tensor I, then you have lots of degeneracy because you have a tensor I here. And when you have a degeneracy, then instead of measuring the lambda I basis, so for the lambda I that has eigenvalues, so some lambda I and lambda j has eigenvalue, then you need to use a projector. Okay. So you will project it onto the subspace instead of project onto individual eigenvectors. Okay. So degeneracy. Yeah. And yeah, so when you have that, then you want, so you have some, so say this is equal to p lambda, then your psi, let's write beta. Okay, so say this thing is p lambda, then your psi measuring in lambda will become like p lambda psi. That's what we mean. Okay. So yeah, so that's the thing happening here. So measuring this lambda equal to +1, your psi become the projector onto the +1 subspace of your state. Okay. Okay, and yeah, that's the physics value measurement, and finally we have a generalized measurement. You can it's just whatever set of matrix Mi here. And they need to satisfy this complexity relationship where some mi dagger mi equals identity, and then short way to remember the measurement result is so getting outcome I, your state become mi psi. So psi become like mi psi. And then you can calculate the probability here. Probability is the known square of your matrix. So known square matrix like this. So psi mi dagger mi psi. And then your actual outcome state is your normalized state. So you need to divide by the square root of probability. Okay, so those are measurements in the quadrant. There will be measurement quadrants just like there are in homework. Okay. And okay, so let's talk a little more about polys. As we say, poly are those x, y, z, also written as sigma y, sigma x, sigma y, sigma z. And they have seen that they have this strong relation on block sphere. But anyway, let's talk about algebra on difference. So first, they have this interesting property that the anti-commute. So every x, y, so every two different of the anti-commute means that x, y equal to minus y, x. Okay, so you switch the order of multiplying two of them and it becomes negative sign. And also, you can derive a lot of their property from their eigenvalues are plus 1 and minus 1. So all of them has eigenvalue plus or minus 1. For example, z here, obviously eigenvalue plus 1 and minus 1. And then you can generalize the poly a little bit on this block sphere. So you have this XYZ sphere, and you think about any point on the sphere. so you have a unit sphere, and you have a point on it and divide. So it's denoted by some vector v with vx, vy, vz. And then think about this interesting matrix. That's a v inner product with the sigma vector means that you have Vx times your sigma x plus Vy times your sigma y plus Vz times sigma z. Okay. And you prove your homework that so for every unit vector v, this v dot sigma is kind of like a poly. Okay. And it has eigenvalue plus 1 and minus 1, so just like a poly. Yeah. And and from here, then you can know a whole bunch of things like the matrix square to identity and the trace to 0, etc. Okay. And yeah, question. Okay. Or preface. Okay. And then we go to spend a lot of time on the density matrix. And so the density matrix, we start with the motivation as a classical mixture of quantum state. We find out that that's not usual quantum state, right? So like where probability of getting some quantum state psi 1, probability of getting some quantum state psi 2, etc. And you cannot describe that as just another pure quantum state because that's not a superposition of quantum state. And we find out that a good way to describe them is by this density matrix. So you have the probability times the projector onto each quantum state. And you sum them together, you get some matrix called density matrix. And so some example, let's see, what do we want? Okay, probably the one as before. So we have 1 over 2. So we'll probably 1 over 2 getting 0 state, and then probably 1 over 2 getting plus state. And then rho will be 1 over 2 of the 0, 0 projector plus 1 over 2 of this plus projector. 1 over 2 and this projector writing matrix form actually like this. 1 over 2 and the plus give you 1 over 2 from order 1 over square root 2. And 1, 1, 1, 1. And so this become let's see which we want what, right? 1 over 4 probably. 1 over 4 and 1 over 4 is 3, 1, 1, 1. Okay. Okay. So that's a density matrix correspond to this ensemble. Okay. So this ensemble of probability and a state pair. Okay. And we see that the density matrix actually totally describes. So this is something you can calculate from the example, and but we found out that the matrix actually describe everything you want to know about example. So first you can do the evolution with this matrix alone. So so if you evolve the ensemble under some unitary, then the density matrix will become this U row U dagger. Okay. Because you think about psi, psi get evolved by U become U psi. Then rho is like a psi ket, psi bra, so psi ket become U psi and psi bra become psi U psi. And so let's say, okay, let's do a hard calculation. So evolve rho with x, right? Then it become x rho x dagger equal to x rho x, and it become so 1/4 0 1 1 0 3 1 1 1 0 1 1 0, and this is okay. So now this is hard. I believe it's well, one of them swap row and one of them swap column. No, but I need to remember which one swap which. Well, I don't really need to remember, but I believe the first one swap column. So 0 1 3 1. So this is going to be 1, and this is 1, and okay, so this is 3 1. Okay, so first one swap row and the second one swap column. 0 1 1 0. Okay, and yeah, so it's 1/4 1 1 1 3 like this. Okay, so that's an example of the calculation. And okay, then we get lazy, and then you can do measurement. And so measurement, there are also different kind of measurement. So you want the expectation value of some Hermitian operator A, then you just trace over rho times A. And then measurement with, if you do generalized measurement with set of measurement operator, then then the post measurement state is like mi dagger, and the probability will be traced over this thing, and so you normalize by dividing this with probability. And yeah, so actual state is this divided by the probability. And we also think that you can characterize what things are density matrix by just checking whether trace rho equal to 1 and the rho is PSD. Okay, question about density matrices. Yeah, and then we talk about this interesting operation of purification. Yeah, where we say we have density matrix rho A, then we can find some psi A B, that's a pure state, where and you trace out B part, it will become a rho A. And it's not unique, but one way of doing this is you write rho A in the you write okay, so we haven't so we're in funny order, but it's okay. Anyway, so one way to do this is you diagonalize A. Okay, so diagonalize A equal to eigenvalues and eigenvectors, and then you write your psi A B just as the summation of the square root of the eigenvalues, and then eigenvector lambda I here, and on the second register you just put the computational basis I, so like a different I here. So you can, so you have like a freedom here to pick whatever basis, freedom. So you just need also no basis here, so that's why it's not unique. But yeah, this is one way to do purification. And and okay, I think we can leave here. So we won't say any also. So obviously one way is to do also computational basis, and by every also normal basis work. Okay, on the second register. And that's because when you do reduced density matrix, so you think about So you think about how to get from side AB to some row A. So you have this reduced density matrix is you do partial trace operation. And yeah, so you get a density matrix on two-party row AB, and then you want to know is reduced density matrix on the A part. That is you trace all the B part, and so basically you do this thing. So remember, trace is you sandwich the trace of a matrix is where you look up the diagonal element of the matrix, and as same as you sandwich with all the basis element I of A, and summing over all those I, and then we do partial trace. So so we do this sandwich with I only on the second register, and then we just tensor identity on the first register. So partial trace is like this. And yeah, so we also have a whole bunch of different different notations to do the partial trace. For example, I believe we also have like row A tensor psi-phi. If you do partial trace on this thing, then equal to row A, and times okay, yeah. So you can remind yourself of partial trace, and then trace of matrix of this thing is just, so you can do cyclic thing, and so it will just be inner product between phi psi, like this. Okay. So yeah, there are a whole bunch of ways you can do partial trace, and also interesting thing here is the stream decomposition. That is, you have any pure state, so it's important that it is pure here. So for pure state psi AB, then you can always write it in a spatial decomposition that's called streaming decomposition. That is summation I lambda I and some orthogonal basis element IA on A part and some orthogonal basis element IB on B part. And here, okay, so here we have a little errata of what we talked in the class. So we say that the streaming decomposition is unique, but it's a little off. Okay, that's because we do the singular value decomposition. So it's like we do diagonalization. So diagonalization of a matrix is most of the time unique, but except when you have degeneracy, like we see here, right? So sometimes you have degeneracy on eigenvalue, so diagonalization is unique. So similar thing happen in streaming decomposition. Okay, so those lambda i's are kind of like an eigenvalue, so those lambda I coefficients are unique, but the basis of this streaming decomposition can change if you have degeneracy on those lambda I. Okay, so almost unique. Okay, so that's streaming decomposition. And that's about what we know in density matrix in equation. About on time. Okay. And yeah, then we have this big O notation in classical computer science that we need to remember. And so quick, wait, we think we, oh, I forgot one of it. Okay. So I should write bigger than constant, right? Okay. And yeah. So we have this class of functions that we think about how they grow, and then we think about exponential function grow much faster than polynomial function, then grow much faster than I written this in funny notation, so this should be log x, okay, and much bigger than log and much faster than constant. And then once again, as a reminder of the notation, so we have f equal big O of g, then that means f is much less than g, and f equal to big omega g is, okay, not much less, it's like f grows, so like g is the upper bound of f, so f is less equal to g, and sympathetically up to down constant, and also this big omega means roughly means f is greater or equal to g, and big theta means that they are roughly equal, and the tilde means asymptotic and up to constant. And yeah, for detailed definition, go see the previous notes. Okay. And finally, we have a circuit. And yeah, so we didn't talk all about the circuit, but remember we will see these kind of questions, so we are given input, and then you go through circuit and want to see output. So for the example, we have a circuit of getting the Bell basis here. 0, 0, then go ahead and mark a plus here, and is C naught will entangle the plus with 0, then get beta 0, 0 out. Okay. And then also we see sometimes it's nice to do circuit calculation with this algebra. So for example, we want to see what the computational basis that ABC go through the circuit become, and okay, so here we have a good easy example. We don't hit it mark, so so let's say ABC. Anyway, so ABC goes through this, then you see ABC goes through the first C naught, then the second register become B plus A, and then go to another C naught, then the third register become C plus B plus A is A plus B plus C, and then finally it goes through a Z gate, so you get a -1 on the first -1 to the first register, so it's -1 to the A, and the same thing, A and the B plus A and the C plus A plus B. Okay, and okay, so I guess that's all for the review. And here we have something that we didn't have time to talk about, so that will be on your final. So this is for final. Okay. Yeah, and I believe we can stop here for now. So anyone has any question? Otherwise, oh yeah, sure.
We're allowed to bring a sheet of notes.
Yeah.
Is that an A4 paper?
Yeah.
Front and back or one page?
Huh?
Is it front and back or?
Yeah. I think either one is fine. Yeah. So, yeah. So yeah, we won't really check the paper, but I think that even if if the paper is too large, it's hard to use. So up to you to decide which. But I think A4 should be okay.
And do you think we'll get the grading from last week's homework before?
You should. We haven't. Then yeah, I will pressure the pressure TA a little bit. Yeah. Yeah, sure. The grading, if it's done, will be better. Yeah. Sure. Okay. If there's no other question, then I think we can stop now. Okay.